Hi everyone, my name is Ivan.
And today we are going to talk about choosing a modern database management system in 2024. So I'd like to start with explaining why I'm giving this talk. So I work in this data infrastructure industry for well over a decade, and I really enjoy talking with people about their data infrastructure to understand how they ended up with their particular solution to this data infrastructure, what works for them, what doesn't, and basically this talk is a set of highlights from these years of experience, both hands-on and from these kind of discussions. So I worked on a handful of database products in this period of time. Two of them are open source. So I worked for 7 years at ClickHouse. You heard all about it if you were here before lunch. And my current role is Vice President, Product and Open Source at YDB. So unlike most other talks in this room today, my talk will be more like overview of our little database market. And we'll start with trying to understand how people approach choosing DBMS in general. And then we'll switch gears a bit to take a look how database world interacts with open source world and why it matters. And finally, we'll dive a little bit deeper into what changes in this process of choosing DBMS technologies as your projects or company grow in terms of data volumes and query rates. Let's jump into it. I like to use analogies that choosing a database management system is quite similar to choosing a car. What I mean by that, at a very high level, all products in both of these markets serve the same purpose. So similarly to how cars move things from point A to point B, similarly, databases take your data, store it for a while, and return back to you with some modifications along the way. But if you take a closer look, you'll see that there are several major categories of these products. As you can see, different kinds of cars here. There are different kinds of DBMS for different kinds of workloads. Hence, they're suited for different use cases. And inside each category, there are usually hundreds of particular technologies out there, similarly to like hundreds of car manufacturers. There are like, I think, 400 DBMS products currently on the market, and which each with their own unique blend of trade-offs and advantages and disadvantages. And even if you look at one particular technology, there are tons of nuance how you can implement it, a lot of options, a lot of deployment ways, and so on. So it's kind of a deep industry to dive into. On the other hand, like similarly how most people drive cars without really understanding how they actually work, similarly you can use the DBMS just by having a general idea how they operate, and that's what I'm trying to cover today. So the most fundamental way to categorize DBMS is the following. It comes from this logical concept of a table, as most databases operate on concept of a table, even though some of them provide higher level abstractions like documents or graphs and others. Most of this trade-off still applies. And basically, the tricky part here is how you map this two-dimensional space of a table with rows and columns into a single-dimensional space that computers provide, both in random access memory and on disk. So, and two diagonal approaches of this is you can go row by row and thus store columns of each row nearby consecutively, or you can go column by column, as you can see on the right, and store one values of one column, then all values of another column. And as we can see, we'll see on next few slides, these approaches dramatically differ the complexity of running a given queries against the same data set if it's stored differently. So the row-oriented approach usually works best for OLTP or online transactional processing workloads when you change small subsets of rows frequently, and column-oriented approach works best for analytical workloads where you kind of analyze lots of data to produce smaller reports out of them. So let's imagine an example website also about cars that has a page that shows all information there is about one particular car model. So to render such a page, likely this website will use a query like this that basically fetches one single row by its identifier it took from URL. So, and as you can see on the right, if all columns of this row are stored consecutively on disk or in memory, it basically translates to one read to render this page. But if you imagine if it was stored in the transposed way, to render such page, you'll have to make reads proportional to the number of columns and kind of reassemble this row on the fly from cells you got from different column files or whatever you store on disk or on memory. And the same website could have another page that shows some aggregates over all models that they know about. This is a bit oversimplified example that uses only one column. In real life, it's usually a few columns, and usually there is some sort of date involved to show a graph or something. But you can see in these cases, it's really beneficial that you don't really care about like model names or other data you have about these cars to produce this report. So it's beneficial that on disk, all values of price column are stored nearby, and thus you again like can do only one sequential read to build such report, and also such layout is really friendly for modern CPUs to run aggregates over such data sets. As you can see, even on such simple examples, there are use cases for both kinds of databases. And the question is what you are going to do about it. So the most simple approach that most people start with is just choose one DBMS. Usually it's transactional DBMS, and throw all kinds of workloads you have on it. But as we have seen previously, OLAP workloads will behave likely slow and inefficient. So it will work only for a while until your data set is small or until you have many users. So at some point you will have to resort to option number 2 or number 3, which we'll explore in a moment. So when you try to integrate multiple DBMS together, you'll have to build some sort of pipeline that kind of moves data from wherever it originated from to your databases. So basically, there's a whole profession that's dedicated to building this kind of pipeline. It's called data engineering. So I just give here a few examples of how these pipelines could look like. So the ones on the top, they treat DBMS as equals and try to concurrently put data in both of them. And the options on the bottom treat transactional database as main one, and asynchronously copy data to an analytical database for further processing. And options on the left try to be as close to real time as possible by introducing an extra component of a persistent queue that kind of buffers the incoming data before it gets put into its destination. And options on the right don't do that by making pipelines simpler, but it introduces extra latency to do everything in batches. So alternative to this is to try to find an all-in-one solution. So the idea is quite simple. You basically build a database that can store data in both ways, and automatically help you kind of decide how to process it in both kinds of workloads. The idea is simple, but implementation is not. So most current implementations on the market have huge drawbacks. For instance, quite a lot of them are commercial and cost prohibitively expensive, like most companies can't really afford them. And other ones, for example, often really focus on only one side of things and implement the other kind of workloads as a kind of afterthought, just to tick the checkbox and use that they have this as in marketing. And that's also what we're building at YDB. So we're aspiring to become a leading HTAP database. It's also quite a lot in progress for us. And as an extra step, we're also adding a persistent queue component in the same platform to kind of simplify moving data around these different kinds of tables or in and out database, and also in transactional manner between both queues and tables. So let's change gears a bit and talk about why open source matters in databases. And the first main thing is that data is so crucial to most businesses that you need to think about how much you want to rely on your database vendor to store your data. So some people often think that, like all these huge companies that everyone knows, like Google's, Microsoft, Amazon, whatever, will be around forever. So they are so huge that they are not going anywhere. So I can trust my data to them, and I'll be fine. But real world shows that even the whole company might be there. It might decide to leave your market, or they might jack up prices like tenfold to become prohibitively expensive. And hence, people start considering for this critical piece of infrastructure like databases to move towards open source. So either you use existing products and maybe you leverage someone else's help just to implement them and build internal expertise over time. And that's actually how communities are formed, by people implementing the same technology in their different companies and different use cases. And some companies can afford to even build their own database management systems. That's actually how both ClickHouse and MongoDB started. And then if you actually build such cool technology that the world can benefit from, please consider open sourcing it as well, because together we can move them faster. And another important topic on this intersection between database and open source is licensing. So historically, many open source projects were also having so-called viral open source licenses. Basically, this means that all modifications to a given technology need to be distributed under the same terms, which is good for sustainability. But on the other hand, it kind of limits usage of such technologies inside large commercial companies, and they often have limitations on usage of such technologies. And that's why my favorite kinds of licenses are permissive licenses. So both YDB and ClickHouse are under Apache 2.0, which is one of the most permissive licenses out there. And then there is a separate story around source available licenses that became popular like during the last few years when database vendors try to protect themselves from larger competitors by introducing licenses that look open source because the source code is visible publicly, but on the other hand, they limit how this source code can be used, which kind of abandons open source philosophy and principles. And I guess everyone has to decide for themselves whether they are okay with such compromise or not. And let's get into the last part about what changes in this database choice process as data volumes grow. So we'll consider 3 stages. When you're just getting started as an open source project or as an user of an open source database, the key point is don't invest too much time into choosing the perfect one that will serve you forever. Because it's easy to think that whatever idea you have you are building will be super popular and is too optimistic, but it's a pitfall, and in reality most projects actually get thrown away after a while. So it's important to actually make the business right, to make sure that you are building something useful and there's demand for it. And on small scale, any DBMS will work fine, and if you don't miss the chance to replace it until it's too late, you'll migrate fine to proper technology that will support you long term. So if still you are getting started and want some specific recommendations, here are a few I'm really familiar with. So the typical approach is to take a standalone database server and use it. Everyone knows OLTP ones, Postgres and MySQL. I still believe the ClickHouse is the one that will get you the furthest in terms of single node analytical capabilities. And if you are interested in this HTAP story, try YDB. But what I really wanted to highlight here is this left column of embedded DBMS. So the difference here is that unlike database servers, there are libraries that compile into your application or gets imported in some other way, which allows you to kind of lower the number of components you need to manage on this early stage, which is really beneficial, which lowers the load on your DevOps team if you have one, but likely you don't even have the DevOps team so early. And thus your engineers won't really need to maintain a database server in addition to your application. So check those out. It's really good for getting started. On the growth stage, that's when you confirm that whatever you are building makes sense. There's demand for it. You might, if you're a startup, you might get investments and try to kind of start accelerate your development. And at this stage, everyone tries to to run fast towards your goal ambition, and the easiest way to screw it up is to start running in different directions. That's why it's really important to take a moment to consider your requirements and discuss it with your team, and ideally put the requirements in writing so you know which data sets you're going to have, what kind of workloads you're running against them, and that will help you actually figure out which technologies might be useful for your use cases. And after this, once you have in writing your requirements, the next step is more straightforward. So you likely have infrastructure from your previous prototyping stage, and then you need to evaluate it against these requirements, and you'll either see that everything is fine and you can plan to migrate to some other technologies later on with some maybe 1 or 2 years plan, or half a year at least, or there are some weak links you need to replace immediately and try to figure out some emergency actions to take to kind of avoid getting overwhelmed maybe by growing demand or whatever is happening in your situation. There are a couple more things to consider on this growth stage. One is the kind of DBMS you're choosing. So historically, most DBMS that are around for 30 plus years, they're developed when most databases were single node, and they're designed for this use case where you're basically bound by what a single server can do. But over these decades, data volumes grew much faster than capabilities of a single server, and hence most DBMS that are developed in 2010 and after are distributed DBMS designed to grow to capacities larger than a single server can handle. And there are like, the trade-off here is that there's less information of these technologies out there just because less time passed. On the other hand, it's much easier to grow with distributed DBMS compared to trying to build something on top of single node older technologies. And another interesting topic, I have no time to even try to cover it here, but the topic is so-called consistency phenomena. So it's easy to imagine how a database should behave. It should be kind of similar to a diary or a notebook, physical one. So you kind of open it, write some data, and close it, and expect it to be there again once you open it again a few times too. But in reality, even single node DBMS don't give such guarantees and often allow for some weird behaviors. You might see your data disappear temporarily. You might see duplicates of it. You might see data that you only thought about writing without actually writing it and stuff like this. And basically, the idea here is if you are using databases, check what it actually guarantees. It's possible to work around all these weird behaviors on the application side, but you need to be aware of this and do it. Otherwise, your end users will see these odd behaviors in whatever product you're providing. And if you're a student, this is also a cool research topic. Consider this for your graduate work because there's a lot of stuff to be uncovered here. On mature stage, there are also tons of things that might be interesting in this aspect, but I want to highlight one. I call it exponential complexity growth. So as we have seen previously, even one integration between two databases might be complex, but let's imagine we had one team who chose some technologies, and now we have another team who independently choose some other technologies. Well, some technologies, and likely there are other different. And over time, in large companies, there are use cases for integrating different data from different places. It might be direct federated queries or some sort of APIs between them. But ultimately, for example, you might want to build a report of e-commerce site, or report of where people spending the most money come from. And for this, you'll need to use data from one team who is responsible for front end to know where people are coming from, and then people from back end to handle purchases. Basically, that's how these errors arise. But which large company has only 2 teams? So in reality, it quickly gets to something like this. So if you pay attention, you'll notice that it's not really exponential, but it still feels like it because nobody really understands how your data infrastructure of the whole company works, how to add one more arrow, and people who develop some of these arrows are gone and all work elsewhere now. So, and to avoid this mess, I'd recommend to invest into building your own best practices, how you run data infrastructure. So choose few technologies that work and try to evangelize internally to kind of stick with them and help other teams to adopt the same tech stack you kind of, most of you kind of adopted. So let's sum it up. So how to choose a modern DBMS? Assess your requirements, data sets, workloads you have or going to have in near future. With this set of requirements, try to identify a few technologies that seem to work for these requirements according to what vendors claim, and then try to actually reproduce these results in your own workloads to see that these claims are actually correct and indeed you can achieve what you're supposed to. And ultimately, once you settled on a few key technologies that satisfy your needs, try to stick with them and make sure the rest of the company, as much as possible, follows along. So that's it. If you have any question, connect with me on LinkedIn. If you're interested in MongoDB, we have a booth downstairs. Step by if you haven't yet. Unfortunately, I'm leaving after this soon, but I live nearby. If you want to chat more, I can come back here. So thank you for your attention. Thank you for organizers.
Thank you so much. We do have a couple of minutes for questions, but before we do that, is the next speaker in the room, please? That would be Peter Farkas. Aha. Peter, could you please set up while we do some Q&A? All right. Questions for Ivan? No? Excellent. I have one. So I might have missed, we had some organizational things, so I may have missed a detail. The part of the problem with doing transactional and analytic is the tendency to store in the 2 different ways, the row-oriented and column-oriented. Did you explain how YDB is dealing with that as a hybrid?
Well, it's not supposed to be talk about YDB, so basically there are multiple ways to do it, and we're exploring like most of them. So one is to basically store data in multiple copies and kind of smartly decide like where it goes. Currently, we're only building blocks for this, but that's kind of the ultimate goal. And actually, that 2 approaches are not like the only ones. So, for example, it's possible to store data in Z kind of fashion, like store a few columns together and a few other columns together if they are used together frequently. That's usually referred to as column families. We have that too as well if you need it. So, like, there are many ways to kind of.
Sorry, I grasped the 4 major schemes. If you weren't answering on MongoDB, that explained. Right. Any other questions? Going once? All right. Thank you so much.
Thank you.
All right. Next speaker is on in about 5 minutes. That's 2 p.m. Peter Farkas, co-founder and CEO at FerretDB, who is going to talk to us about MongoDB alternatives, and is there a need for a new open standard? Spoiler alert, I think there is.
Thank you. All right, well, welcome everyone. Thank you so much for joining this lightning talk, I guess. We have 25 minutes to go over a lot of topics. First of all, let me ask you some questions. Who uses MongoDB from here? Raise your hand. MongoDB users. Okay. Postgres users. Come on. You don't use Postgres. Okay. Who knows what is the difference between open source and open standards? What is the difference? Is it the same thing? Raise your hand if you think it's the same thing. Okay, well, at least there's that. So I'm going to talk about open source, open standards, and the history of SQL. And I promise that this is going to make sense in the end. About me, my name is Peter Farkas. I'm the co-founder and CEO of a company called FerretDB. We are a MongoDB alternative built on Postgres. So we turn Postgres into MongoDB. But this is not going to be a sales plug. So let's say this much about FerretDB now. I worked at Cloudera, Percona, and various different open source companies. Been working in open source for 15 years. And I'm Hungarian, and I live in Spain. So we will do a very quick recap on open source. I will skip a lot of slides because I'm sure you're familiar with what open source is. And we are going to talk about open standards and some examples related to these. So why open matters? I think Ivan had a very good presentation just now about the importance of open and open source, especially if you're considering a database to use for your use case. But very shortly, it promotes innovation. Open source projects can work together. It's transparent. It's more secure because you know what's in it. It's about collaboration, and it's also sustainable, because you don't have to redo a lot of work which others already did. You can just use it. And this helps a vendor lock-in. Now, there were not a lot of hands in the air when I asked you about the difference between open source and open standards. So this is a very, very simple example here. Open standards are the blueprint, and open source is the implementation of the blueprint. What this means is you can use open standards to build something which can interact with other solutions out there on the market, and it is going to tell you exactly how to interface with other applications. And it doesn't mean that open standards should always be implemented with an open source license, so you can do it in a proprietary way as well. So I'm going to skip these because this is the last day of an open source conference, so I would be surprised if this would be anything new to you. Open source is software which is licensed under an open source license. It's not just anything you claim to be open source. It needs to comply with the open source definition, which says that the license which your software comes with needs to comply with these 10 points here. For example, you can't discriminate between users when it comes to location or use case or whatever else, and some other stuff as well. I'm sure you're also familiar with these. Examples of open source software and hardware. So if you look at this slide, there are a lot of familiar logos here. I'm sure you used VLC Media Player or Android or Mozilla Firefox. What's interesting about this slide is that some of the logos here would claim that they are open source, but they are not. Elastic and MongoDB would be two examples, but there are many more. I feel bad for singling them out, but hey, that's life. So why do you think these two are not open source software, even though they say they are open source? Any ideas? Well, why?
They violate the no discrimination on user or endeavor by limiting uses.
Yeah, so basically they violate the open source, the 10 points of the OSI requirements in order to consider something an open source license. So even though they are calling themselves open source, they don't come with the same freedoms as the other software would go. Open standards. So we established that open source is mainly software and it's licensed under an open source license approved by the OSI. This is what we can claim as open source. So what are open standards and how are these born? If you remember, this is the blueprint which you need to use in order to create software which can interface with other solutions out there. There is a list of definition for open standards as well. It came from the same person originally as the OSI definition for open source. The author is Bruce Perens in this case as well. And it's pretty much about the same thing. So open standards should be available to implement by anyone. It should be open. You should be able to read it, implement it for free, and no one is allowed to have any claims for your work if it's based on the open standard. That's very, very important because open standards are really there for all developers to make it possible for others to implement and innovate using something which they came up with. Examples of open standards. So this is where the difference becomes more visible. So you see some logos here and some file extensions. If we look back to the previous slide with the logos of open source software, we've seen implementations. Mozilla Firefox is an implementation of what? It uses the HTTP standard very heavily, or the CSS, or the HTML5 standard in order to show you web pages on the internet. So without these standards, it would not be possible to create a web browser, because I don't know if what the age group is of the audience, but some of us would still remember how painful it was to create a website in the 2000s or 2005, because all of the browsers were following a different standard when it comes to HTML, when it comes to CSS and the others, and you were not able to create a website which would look the same way on all screens. And open standards help with that. One example, or one other example, is comma-separated values. So the power of open standards would be that, for example, if you create a tool which sends out newsletters to a contact list, and you have competitors as well, you have other tools on the market which would do the same thing. With comma-separated values, your user can actually download the list of contacts, maybe 20,000 contacts of newsletter subscribers, and import into your tool, which means that open standards foster innovation, and they make competition stronger, which is great for users. And this way the market expands, because the users are more confident that if they choose one product, they will still be able to move away from it if it turns out to be bad. So for you developers, this is great, because you have a chance to compete on the market. And for you as users, this is also great, because you can make sure that you're always using the right tool for the problem, for solving the problem you have. There's a very interesting example, the portable document format, or PDF, which is also an open standard, but it was only standardized in 2008. And before 2008, you were only able to open a PDF with software which was licensed or developed by Adobe. And if you can see on this graph, up until 2008, the popularity of PDF was dwindling. It was basically dying out because you could not be sure as a user or as a software developer that if you implement PDF and you pay a license to Adobe, will they raise the license fee in a year from now? Or will the file format change in a way which is not going to be good for you or for your use case? And in 2008, it became an open standard. And from that point, anybody could implement PDF and anybody could read and follow and build on the standard. And this is how you can just book an airline ticket or save your file in PDF, and you can open it with software which has nothing to do with Adobe. Did Adobe lose by letting PDF go and make it available as an open standard? No, because the popularity of the file format increased a lot, and the market basically grew into multiples of its size before 2008. How open standards are created? So it's different than open source in the sense that usually standards organizations are involved. Standards organizations create space for multiple vendors in a given area to collaborate together and figure out how a standard should look like, how the protocol or anything else should behave and interface with other solutions. These are related to governments, and I'm sure that you have heard at least one of them in your life. Standardization bodies are special because when they discuss a standard, they create a standard, everyone has a say in how it should look like. So it's an equal discussion rather than Adobe saying, hey, this is how it's going to look like, and that's it. So it creates an environment where innovation can be detached from a particular vendor. And that's how it prevents vendor lock-in. I'm sure that I made this point multiple times already. If anybody can build on this, then there's less chance for some entity to grab the market for itself. Very quickly, the story of SQL as an open standard. So this is by far not going to be a history lesson because we have 10 minutes to go, but I felt important to mention SQL here because I'm sure all of you are familiar with it, but a lot of people are not aware how it came to be. So the short history of SQL, it was created by IBM. It was created by a person named Edgar Codd, who worked at the IBM Research Center in California, and he came up with the relational model for databases. This is the model which pretty much all databases, all relational databases are built on. He came up with the way how we think about databases at present. The problem with his invention, this was in the 1970s, is that he also came up with a query language for it. And that query language was not as understandable as SQL is. You pretty much had to be a software developer or a mathematician to query data from a database, from this new relational database he envisioned. So there were two other individuals, Don Chamberlain and Ray Boyce, who came up with a query language which is a lot more simple and can work with relational databases. This was also in the 70s, and together with the relational model and SQL, we got a powerful tool called databases. I mean, for decades, database equaled a relational database, which probably used SQL. But how that happened is very interesting. So a very sad addition is that Ray Boyce was, I think, 27-year-old when he published the document on SQL as a query language, and about a year later, he suddenly passed away. So he never learned the huge impact he had on the database world or the world of IT. So after IBM essentially came up with the relational model and SQL, they implemented it, they called it IBM DB2 as a product, and it only ran on these huge washing machine sized computers. So if you wanted to use SQL, if you liked the thing, then you had to buy one of these, which is not great. So this is the essence of vendor lock-in. You could only get SQL from IBM. And then, since other vendors liked the idea as well, they started copying IBM DB2. They made their own implementations of SQL, Informix, Oracle, Sybase. They all came out with database products which used SQL, but they had very different ways of implementing it. So you couldn't be sure that you can run a simple SQL command across all of these different products, which means that without an open standards, the users still face vendor lock-in. If you started using IBM DB2, even though Informix or Sybase also used SQL, you couldn't just migrate to it because it was not based on an open standard. So many different dialects and no conformity between these products. And then SQL became an open standard in 1986 or 87. It became an ISO and worldwide standard recognized by many standardization bodies. So anyone could implement these, and that was the start of the rise of relational databases and SQL, because open source came, and open source database projects adopted SQL. Postgres, I think before 1995, was not even compatible with SQL, so you couldn't run SQL queries on it. But they implemented it, MySQL came, SQLite came, and then hundreds of other derivatives appeared, and that's the world we live in today, where we just take SQL for granted, we can run a query anywhere we want, and it's going to work similarly across multiple different products. So what is open source without a standard like? And this is the reason why I chose to talk about MongoDB today. So MongoDB had a very similar story to SQL and IBM DB2 in a sense that they came up with a query language and they came up with a new way of storing data in a database called the document database or the document model. And their tagline was that you don't need to be a database administrator to run a database. So this is supposed to be even more simple, easier to query, easier to use, easier to learn compared to relational databases. We can argue whether that is true or not. That's not the point of this presentation. But this was open source. Everyone was able to use it, but only MongoDB implemented their own query language they came up with. And it went proprietary in 2018. So after they captured most of the market of document databases, they just shut the door and said this is no longer, well, truly open source, and they actively work against companies who implement the wire protocol they came up with. And the big problem and the point of the presentation and the reason why I talked about SQL is because I wanted to show what it is like when you build on something with no open standard behind it, and that would be MongoDB, because you can only get MongoDB from MongoDB nowadays. This is a familiar slide because the relational database slide was very similar in a sense that when MongoDB went proprietary, a lot of alternatives appeared on the market. Oracle, Microsoft, AWS, Huawei, they all came up with implementations for MongoDB because they wanted to use the MongoDB query language and document database as a concept, but they couldn't use it anymore because of the license. They couldn't provide it anymore because of the license. They came up with their own interpretations of the MongoDB query language, the MongoDB wire protocol, and this led to the exact same situation as we had with SQL in the 70s. So history totally repeats itself, and users of MongoDB found themselves in a very similar situation as we've seen with relational databases in the 70s. Or, well, we haven't seen it, but we know how that happened. So the issue is the same, different feature sets, different degree of compatibility between these alternatives, meaning there's no way to migrate very easily between them. So we think, not just we at FaradDB, but many others think that we are in need of a new open standard for MongoDB and the MongoDB query language, a standardized core feature set based on MongoDB, a JSON query language, a standard similar to SQL, which describes how MongoDB queries should look like and how they should behave as a database. And it would ensure the same degree of compatibility, portability between document database products as we have with SQL. So this is the point I attempted to make today. We believe that this would be very good for users the same way as it is good for relational database users as well. So FaradDB, I promise that this is not a sales pitch. Well, something's wrong with this slide. I just wanted to mention our solution to this is we turn Postgres into a MongoDB compatible database. FaradDB runs as a proxy on top of Postgres, and we hope, we believe that this implementation, okay, there we go, is going to be a basis of a new standard across many different products. We release this in open source license, Apache 2.0, and we hope that MongoDB users will be able to move from MongoDB to Postgres this way using FaradDB. In fact, many did. We have lots of users, over 8,500 stars on GitHub. So please find us as well in case you're using MongoDB and in case you also got the point that something needs to be done. Thank you so much. Any questions, perhaps?
Thank you, Peter. Before we take questions, is Konstantin from Percona in the room? Could you please set up while we take questions? Thank you. Okay.
Thank you for your talk. Actually, I have a question to the room. Have anyone actually read the SQL standard? Like the whole 1,000 something pages? And the question, what do you think about the fact that you have to pay the ISO to actually read it? So it costs like $300. Do you think it's okay practice and should it exist longer term?
Sorry, what was the question? I didn't.
So you have to pay a few $100 to legally read the SQL standard.
Mm-hmm.
And do you think it's a good practice? Why the hell it exists? And should it, for this new MongoDB standard, should we do the same? Or maybe there are better ways to do open standards?
So there's not much we can do about the whole, way how open standards and standards organizations work. I suppose that the reason you have to pay quite a high fee to download the SQL standard is because they are looking to fund their operations through these fees. I don't think it's fair because, of course, you know, the whole idea should be that it's available to everyone, and that it should be free. Debatable. I would hope that if we launch a MQL standard, then nobody would need to pay for it. In fact, we are planning to start the project on this on GitHub, and for sure you're not going to have to pay for that.
I am a participant in ISO, ITU, and IETF standards processes. I have a very particular view. ISO's position is unfortunate.
Yep. All right. Thanks, everyone.
We've probably got time for one more. If there was anybody else wish to ask a question this time? Nope. In that case, I'll offer an observation. I hadn't noticed the parallel between the current state with the document query languages and the situation half a century ago with query languages, but it's even closer than perhaps you have thought about. Because IBM's principal mode of business at that time was the bureau service. Most of their customers didn't own their own machines. They were in IBM data centers. We now call that cloud.
Eerie, isn't it?
It's eerie. We're right back where we started half a century ago. Okay, about 2 minutes before Percona. Okay, next up we have Konstantin, the senior software developer from Percona, to talk to us about key management for data at rest encryption, which is a fitness subject, particularly for Percona.
Hello, my name is Konstantin Trushin. As was said, I'm senior software developer at Percona. At first glance, the topic of my talk can seem wordy, but we can notice that it comprises 3 parts. Going bottom up, there are Percona servers from MongoDB, data at rest encryption, and finally key management. Our discussion will follow the order, so let's jump in here.
Technically speaking, Percona server for MongoDB is a fork of MongoDB Community Edition and maintains backward compatibility with the latter. Percona server for MongoDB implements more features that its upstream. Many of those features, such as authentication mechanisms and backup, can be especially useful in production environments. But today we are going to be talking about securing user data with data at rest encryption. Data at rest encryption ensures that if someone gets unauthorized access to the storage media, they still can't read the user data. It encrypts database files on disk with AES working in one of the 2 chaining modes. Enabling data at rest encryption requires a clean data directory, since already existing database files can be encrypted. The perfect time to do so is when you add a new node to your database cluster. On such a node, whenever Percona server for MongoDB creates a new database, it also generates a dedicated symmetric encryption key for it. On disk, a database is mapped to a number of files, 1 per each collection and index. Percona server for MongoDB encrypts all the data it writes to those files with the generated per database key. The key itself then goes to the encryption key database, which in turn is saved on disk and encrypted with a master encryption key. This 2-level approach enables efficient master key rotation, as we will see later. On subsequent restarts, Percona server for MongoDB first decrypts encryption key database with a master encryption key, and then uses per database keys to decrypt actual user data. The main byproduct of setting the data at rest encryption is a master encryption key, which we need to store externally somehow. On the right, you can see how a configuration file for Percona server for MongoDB can look like if we enable data at rest encryption. First, we should set the enable encryption field and then configure one of the three facilities for storing master encryption key. The simplest option is just to keep the key on a local file. And needless to say, that is not a secure approach and is suitable only for test. We will concentrate on two other approaches, which are KMIP and Vault. Key Management Interoperability Protocol, also known as KMIP, defines a number of object types it can manage. For instance, different types of keys, certificates, and so on. Each managed object under KMIP has a unique identifier, which is a primary means for locating that object on a KMIP server. Among other attributes objects have in KMIP, we are most interested in the state attribute, which is a foundation of the feature we will discuss later. A user can issue a number of operations against the KMIP server, for instance, register to upload an object, get to fetch it, get attributes, and so on. As an alternative for a KMIP server, one can use HashiCorp's Vault to store a master encryption keys. Vault is a server with many different capabilities implemented as a pluggable engines. We're interested in a versioned key value secrets engine that essentially stores sets of key value pairs. Percona server for MongoDB constructs a single entry secret where a master encryption key encoded in base 64 serves as a value for implementation defined key. Before an engine can be used, it should be mounted, that is initialized at a particular path on Vault. Within an engine, a secret is located by its relative path and version. So the secret's absolute path is a concatenation of the engine mounts point, the fixed data word, and the relative path. We can think of an ordered tuple consisting of the absolute path and the version as a compound identifier of a secret on Vault. When configuring Percona server for MongoDB to work with Vault, we recommend to configure each node in your database cluster so it uses a unique relative secret path. For instance, we can deduce a relative path from the host name of the node. By default, Vault keeps 10 versions for each secret. Then, uploading each new version overwrites the currently oldest one. So uploading happens every time we create or rotate master encryption key. In order to prevent overwriting, we should increase the number of kept versions by setting max versions parameter on the secret engine, ideally just after initializing the engine. To configure Percona server for MongoDB to work with KMIP, we should provide a server name, a port, and a pair of certificates for mutual authentication. When Percona server for MongoDB first starts with this configuration, it internally generates a master encryption key and registers it on a KMIP server. In response to the register request, KMIP server returns an identifier which goes to the metadata onto the data directory. As a result, there is no need to specify identifier on the next restart of Percona server for MongoDB. It will read it from the metadata and get the key from the KMIP server. Configuring Percona server for MongoDB to work with Vault repeats the general principles of doing so for KMIP. For Vault, we use authentication token instead of a client certificate. But more importantly, we should specify the absolute secret path in the configuration. On the first step, Percona server for MongoDB uploads the generated master encryption key on Vault and gets under this configured path and gets a secrets version in response, which goes to the metadata together with the path. And on subsequent restarts, path and version from the metadata are enough to fetch the master encryption key from Vault. We all periodically change passwords in our personal computers. And in the same way, we should periodically change master encryption keys in our database deployment. To do so with KMIP, we should stop Percona server for MongoDB and start it again after setting the rotate master key parameter. In this mode, Percona server for MongoDB doesn't serve any user queries, but gets the master encryption key from the KMIP server and decrypts the encryption key database. Then it generates a new master encryption key and registers it on the KMIP server. The new key is used to re-encrypt the encryption key database, and its identifier replaces the old one in the metadata. Then Percona server for MongoDB exits, concluding the rotation. Now we just need to unset the rotate master key parameter and start the service again. At this time, we are already using a new key and can serve client queries. Usually, master key rotation doesn't take much time, because thanks to the two-level design we saw earlier, it only needs to re-encrypt the encryption key database, which is usually small, compared to the whole data set. Rotating master encryption key with Vault is carried out in the same way as it is done with KMIP. When Percona server for MongoDB uploads a new master encryption key to Vault, it basically creates a new secret version under the specified path, that potentially evicting the currently oldest secret. Now, that is why it is important to set a max versions parameter to high enough value. And even if we have all security practices in place, we should still think of the measures we would take in the case of security incident. For instance, if our database deployment has several hundred nodes and one of the master encryption keys gets compromised, we should be able to quickly identify and isolate the affected node and replace the key. Fortunately, Percona server for MongoDB can help us here with its soon-to-be-released feature called key state polling. The feature relies on the state attribute each managed object has and the KMIP. When a secret key is first registered on a KMIP server, it gets pre-active state. And if the feature is enabled, Percona server for MongoDB sends the activation request to the KMIP server right after registering the key, thus transforming the key to the active state. Then it periodically polls the key state to check whether the key is still active. If one of the keys gets compromised, a security engineer just needs to put it in any state other than active. And the affected instance of Percona server for MongoDB can detect that no later than a configurable polling interval and stop the service, signaling that an action has to be taken. And you only need to rotate a master encryption key on that particular node to bring all the database cluster to safety again. Here we briefly overviewed the key management systems supported by Percona server for MongoDB, and you may be wondering which one you should use. As usual, it depends, but there are some things to consider. KMIP is an open standard with many implementations available. However, majority of those implementations are commercial, and thus some licensing costs is involved. The only free and open source implementation I know is PyKMIP under Apache 2.0 license. However, it is more a tool for demonstration and testing than a software for production. On the other hand, Vault is a specific software, not a standard, so you have only a single vendor. On the flip side, its community edition can be freely used in production in many cases. It is also worth noting that configuring Percona server for MongoDB to work with Vault involves slightly more hassle than doing so for KMeep. And interestingly, Vault's Enterprise Edition implements KMeep as well. Probably there is time to draw some conclusions. As with many other security features, we recommend to consider enabling data at rest encryption when you just starting planning your future database deployment, because encrypting already existing cluster is feasible, but can be a tedious task. It is also important to do regular backups of key management system, be it KMeep and Vault, and those backups should capture all the master keys without omissions. And when you are choosing between these two options, you should consider both operational complexity and financial cost of running each of them. Finally, I'd like to present some resources. They are KMeep specification of version 1.0 by KMeep repository on GitHub and Vault's documentation. You can find many more information about Percona server for MongoDB in Percona blog and documentation. And if any questions arise in the future, you can ask them on the community forum. That's probably everything I wanted to tell today. If you have any questions, I will be glad to answer them. Thank you.
Thank you so much. We have lots of time for questions, but as usual, if the next speaker is in the room, I will invite you to come down. Igor from Lithium, are you here? He will arrive in time. Okay, well, in the meantime, the floor is yours. Any questions on this topic? In that case, I have one because I feel like I missed it. The licensing status, of course, is something that concerns me personally, but you talked about a cost complexity trade-off between using a KMeep implementation that's not Vault and using Vault.
Yeah.
Was the complexity just the need to poll for compromise, or were there other complexities that Vault solves?
I mean that from one hand, KMeep seems to be simpler to configure and operate, but however, implementations cost some money. On the other hand, Vault requires more discipline and in operation and configuration, but its community edition can be freely used unless you, I don't know, provide Vault hosted services or compete with the HashiCorp itself.
I'm aware of HashiCorp's approach, and it's quite good, but it's not open source. So I was intrigued to understand what
neither of them can be considered open source because Vault have business source license. KMeep is an open standard as Peter presented, but implementations are not open in most cases, unfortunately.
There aren't any open?
You see, I know one by KMeep. It is kind of tool for demonstration because from my point, security in this implementation isn't on the highest standard.
Okay, that's a legitimate beef. If the only pure FOSS implementations available are compromised choices, then that's an important fact.
And of course, we all would be happy if we had open source, truly open source KMeep implementation.
Something to look forward to. All right. Any other questions on key management for Mongo? No? All right. Thank you so much.
Thank you.
All right. We'll resume at 3 p.m. with maintenance for MongoDB replicas. Okay. Welcome back. Next up we have Igor, principal consultant at Beetle, to talk to us about maintenance of replicas in Mongo. Please go ahead.
Xin chao. Thank you. Thank you everyone for joining this session. And we will be talking about maintenance for MongoDB replica sets. So a few words about me. My name is Igor. I'm based out of Skopje, Macedonia, that's Southeast Europe. I'm working as a principal consultant at PTN, supporting both MySQL and Mongo technologies. I do have some certifications during the years. With the experience, I just tried to see how does it look like when you are challenged to do a certification. I mainly do automation with Bash and Python. Also husband and a father, like to travel and occasionally speak at conferences. So some of my social links here, mainly LinkedIn, Twitter, and also GitHub account. So on our agenda today is explaining MongoDB replication one-on-one, so beginner friendly. Then jump into replica set configuration, some of the deployment topologies. Then we'll talk about replica set maintenance, how to reconfigure, how to make hardware changes or OS patching without any downtime. And we'll have some Q&A at the end. So in the essence, replication is maintaining the same data set across multiple machines. So with MongoDB, it's not different. It's just a group of processes that maintain the same data set. Replication allows us to have redundancy and high availability in case one of the instances goes down, then there is another instance to pick up. With MongoDB, the replication works in a way that there are odd number of nodes that participate in election, and the failover is automatic. So in case the primary goes down, then the two other nodes, in this case the secondary nodes, will form an election, and one of the secondary nodes will be promoted as primary. So if you have odd number of nodes, like 3, 5, then the majority needs to promote an election is 2, then it's 3. If you have 6 nodes instead of 5, you are not adding anything for redundancy because you still need a majority of 4 nodes out of 6. So that's why it's important to have odd number of nodes. And with that, you have fault tolerance. The replication concept for MongoDB is that all of the writes from the application layer go through a driver which connects to the primary. The primary stores the writes into its operations log, and the operations logs asynchronously is copied to the secondaries where the secondaries apply the operations. The secondaries also create operation log locally, and that operation log can be used to sync another secondary. So if there is, which by default is allowed, chaining, the replica set members cannot just ask the primary for sync operations, but also can sync from another secondary, which is a good improvement because the primary will not get overloaded. And by default, the op log, where all the operations are saved, has some defaults on different operating systems. The lower bound is 50 megabytes for in-memory systems, and it's 1 gigabyte for data on storage. The upper bound is 50 gigabytes, but it's configurable. So starting with MongoDB version 4.4, not just that you can set the op log size, but there is a configuration variable that is op log min retention hours. So you can say, I want 72 hours of op log retention, which means that when you write to the database, that write is retained for 72 hours before it's circulated. And the op logs is basically a circular log that gets overwritten. Deploying replica sets. Let's assume we're deploying the basic 3-node replica set where each node will have to be a VM in a virtual private cloud or isolated network physical hardware. We need to create configuration file with some basic options. In the configuration file, there is a section that specifies the replica set name. And using that replica set name, then we go on one of the 3 nodes, we initiate the replica. Once the replica is initiated, we confirm that the configuration in the replica looks exactly how we want to look. And then there is a command to add additional nodes in the replica by doing rs.add. So that is all done from the MongoDB shell connecting to the primary node. And at the end, we finish by running 3-node replica set. rs.status is the command to check what is the current status of the replica set, and it shows what is the status of the node. So there can be primary or secondary, and for the failed nodes, for nodes that are not healthy, there might be different status. Some of the configuration options and limits for MongoDB replica sets is that you can have up to 50 members, and 7 of those 50 members can be voting. There is also option to add arbiter node. The arbiter node is different. It doesn't hold any data. It's there just to participate in elections. And you can have also different secondary nodes by changing the priority, making a node hidden, and delayed. So I'll be covering those right after. The arbiter node is just a process in a replica set. It participates in election. Let's say you have a 3-node replica set, but you don't want actually 3 copies of the node. So you have a primary, you have a secondary. The arbiter is just a single processor on a very light machine where it checks the primary and the secondary. If it loses connection to the primary, it asks the secondary, do you see the primary? The secondary doesn't see the primary, then the arbiter votes and says, okay, now you will become the new primary. It's just for elections. And usually for high availability, if you have 2 data centers, you can experience a loss of single data center. If the arbiter is deployed in a 3rd data center, then it's very unlikely to lose connection between 3 data centers. So data center failure is covered by that as well. Priority 0 node is basically a node that cannot be elected as a primary. If a primary fails, then between the rest of the nodes there is election. All the nodes that are configured with priority 0 will not participate in election to become a primary. So that's priority 0. A hidden node is also a secondary state node, but it's priority 0 and is not visible to the application because the driver excludes hidden nodes to the application layer. So hidden nodes are usually useful if you have some reporting or if you want to run backups. Then you connect directly to the node, do analytics, run backups, but the driver will not see that, so the applications will not get impacted. And a delay node is also a priority 0 node. It is a hidden node. The driver will not see because you set a custom delay where the replication on the hidden node will be delayed by the seconds you specify. So if you want to have a node for disaster recovery, let's say 4-6 hours behind, then you configure a secondary as a delayed, and then in a case of any human error or something that goes bad, you can extract data from a secondary hidden delayed node, and then works very well for disaster recovery. You can even stop the node and apply all operations up to the second or before any human error happened. Like somebody may delete user records and you want to restore. So let's jump into some of the maintenance operations that you may end up. There are different groups of maintainers that think any maintenance should be tested in production. But I believe that if you do a maintenance, it's better to test the plan in pre-production environment like QA or staging or something else. But before jumping into any maintenance, the first thing to do with any database system is actually to monitor what is the status. Because if you don't monitor the status, there might be nodes down, and if you want to do patching, you can start patching a healthy node and stop that node while other nodes are down, and that may cause downtime. So there are tools out there, open source, proprietary software that you can use. In this case, this is a dashboard from Percona Monitoring and Management, which is an open source tool. And here I have some red flags that you should be careful with MongoDB replica sets. Like, for example, the worst that can happen in a replica set is that it doesn't have any primary node. That is definitely something that you want to trigger alerts if you are running a replica with no primary. Other than that, some important things to monitor, maybe not that critical, but if any host in your replica is down, or if you have a secondary that is in recovering state, it doesn't replicate from a primary, or if you have a huge replication lag, all those are maybe not so critical, but very close. And some other just like informative monitoring alerts that if a host restarts out of a sudden, if it reboots, or what is your backup status, like those are not critical, but you want to pay attention. One of the first things that might come up with replica set maintenance is that you may realize that you have a very low replication window, that your secondaries are replicating from the primary, but if the primary fails, then you have like 3 hours then in a replication window to bring up a failed node. So usually that's very low, and there are requests to watch the uplog size, the replication window, and to increase. In older versions, it was more difficult to increase the uplog size. In newer version, that's improved, so you can dynamically just resize the uplog. You will need to do some math. What is your uplog size? How much disk you have free? What is the desired uplog size that you want to increase? In some of the new versions, there is also the variable uplog min retention hours, which you can set, and you just go 48 hours for uplog size, and you have 48 hours always. One caveat with that is you will need to pay attention how much from your disk space is consumed by the uplog, because the uplog may consume a lot of disk space just by setting huge uplog retention hours. Other replica set maintenance changes that you may end up is when you're adding nodes into the replication, sometimes you may need to reconfigure the node as a priority maybe need to change. You may need to put a node into hidden mode, or you need to just delay the replication. So every replica set has its configuration into output of rs.conf. You store that output into a local variable because the MongoDB shell is more or less a JavaScript. And with that JavaScript object, you can do any changes that are required to. Like you can reduce the priority on certain nodes, you can put a node as hidden, or you can put slave delay, let's say 1 hour. Once you do all the changes that are required, the next thing is actually to apply the same config into the replica set. And there is a replica set helper that does exactly that, rs.reconfig, and you pass the object, the configuration file that you just modified. And also with this, if there is not a primary, maybe the primary failed and you're running the replica set into secondaries only, there is also option to use force true. And with that, you're forcing the replica set to accept your modified configuration. So there is also option for that. Each replica set, from a driver level perspective, when the application is connecting, you have options for read preference. And there are multiple read preferences in MongoDB. One is it goes to the primary by default. So all the reads from the driver connected the client application will go to the primary. There is read preference primary preferred, which means if there is no primary, which is preferred, then it goes to a secondary. Secondary preferred is the other way around. You prefer a secondary for reads, but if it's not available, it will go to the primary. Secondary read preference, it always goes to a secondary, and nearest is based on network latency. You connect your driver, and based on network latency, what is the fastest node to the driver, then it connects to that node. And with MongoDB 3.4 and later, to have a secondary node with secondary preferred read preference, it needs to be less than 90 seconds replication lag. So if it goes more than 90 seconds lag, then it goes to the primary. And this is how it look like if you have a global replica set in different data centers or availability zones across the world. So it can be South, North America, Europe, Asia, Australia. You have one primary, several secondaries, but only 7 of those nodes will be voting. So if there is a primary failure, 7 out of the total nodes, which is 50 max, then 7 will be voting. And this is useful because with MongoDB, you can have tags, and tags are something that is applied on a node. So let's say that you have data centers in Europe, in North America, Africa, Asia Pacific. You can tag each member of the replica set with its own data center and what is the usage. So, for example, in Europe, you can have a data center Europe. One node is usage production, the other node is usage reporting. So when the application connects and it tries to find whatever is the document that you are querying, you can specify the tag. The tag will be data center and usage, because that is how, yes? 5 minutes, okay. So You configure that, but you need to be careful, because if you configure your members to have data center and usage, and later you want to query from your driver for a data center and usage that doesn't exist in your replica set configuration, that is like you don't have any node with those tags, and you will experience an error in your application. So it's important to keep an eye on what tags are configured and how do you query from the application. Another thing that might happen for replica set maintenance is that a secondary goes down, it's down for a long time, it joins the replica set, it's losing the upload position, and now you need to resync that replica member from the beginning. MongoDB has that automatically. You just remove everything from the data directory, rejoin it, and it will start initial sync. Or if you have a very large data copy, you can lock another secondary, do a snapshot, restore to the failed node, and they both join at the same position. Similarly, if you're doing hardware or OS upgrades, network changes, anything that may be related to the primary, secondary topology, you start anything that you're doing as a maintenance on a secondary node. If you have hidden, delayed, or priority 0 node, that is the preferred node where you want to do initial upgrades, initial patches, because those nodes are not that impactful to the application. So anything that you may be doing, first do on those nodes, and then while all the secondaries are patched in a round-robin fashion, you step down the primary, and the primary is down as last node. So both secondaries finished, the primary is last. Step down, there is a command, election happens, one of the secondaries will be promoted, and all the steps that you did on the secondaries, now you get to do on the primary. Database version upgrades. Another thing that is usually annual maintenance for a replica set, you need to upgrade to the latest version. So with MongoDB, with the latest version upgrade, which is 7, if you are upgrading from version 6, you need to be sure that your version is current, version 6, else you can't jump from version 5 to version 7. So you need to go one version at a time. And once you're up to version 7, you can't go back before 6. So you can only downgrade to version 6 and not to version 5, which previously it was possible to downgrade multiple versions, but now it's not. And it's the same process. You upgrade secondaries and step down the primary at the end. There is with every new version, there is a feature compatibility that you will need to enable manually after the upgrade. And index builds, same as all other maintenances. You can do index build with a non-blocking operation, or you can do index build by taking out one node, build the index, join it to the replica, and repeat the process. Backups, you log the database on a secondary, preferably delayed node, do a snapshot, unlock the database. So especially in the cloud is very convenient. I have a slide to show how to do implement TLS, but for the purposes of the talk, just a quick summary. So replica set with MongoDB should be run always with odd number of voting members. Hidden or delayed members can be used for reporting and backups. Don't use a single primary mode where all other nodes are with priority less than the primary, so don't prefer a single node for a primary. do any maintenances on the secondaries before applying changes on the primary, have monitoring, have alerting, especially for op-log size, replication window, if a node goes down, do backups, take backups regularly and do restores test, and don't run your database open, enable authentication and authorization. And I'll type in questions.
Thank you very much. So before we go into the break, any questions? I have one little one. You mentioned the option when updating a replica set configuration to force it.
Mm-hmm.
What are the circumstances under which you would want to force or not force? Why is that an option?
Force exists if you want to really push your configuration and ignore what is the state in the replica set. So the replica set sometimes might be in a bad state. You may have a primary failed and there is no primary to elect because there are not enough voting nodes. And in that case, you can force your configuration and that configuration gets upgrade in the version. So it will be the latest version. And it's in those scenarios. It shouldn't be used regularly, but it's just
this is the building is on fire. Yes,
Oh,
I really want to
optional.
fix it this way. Please do it this way,
Yeah.
because I'm certain. Yeah, okay. All right, thank you so much. Right, we now have a break, sponsored by our good friends at Penpot. Please enjoy, and we are back at, I forgot to check, I think 4 o'clock. Yeah, 4 p.m. and we have 2 more speakers before the wrap up. Thanks again.
Welcome back. So, we're into the final sessions of the conference. Our second last session for this track is from King Butcher and Tiger Beetle, just to talk about database
Design from first principles. Take it away.
All right. My name is King Butcher, or Boodle. And before we get into it, let me pose a question that you don't have to answer, but just think about it in your head. If you were to write a system to track money using a database, how would you do it? Like, what's the simplest solution that comes to mind? So you'd probably do something like this, where you have a table that has amounts that affects different users, and the amounts are affected on different types, like withdrawal and deposit. And so something as simple as this works for most cases, but it doesn't work if you want to make anything complex or make anything scalable. Because here, let's say you wanted to compute the balances for something really quickly, like how much money does user 2 have right now? Can't really do that efficiently with this. You have to scan all of them. So instead, you'd probably make a completely separate table to track all the current balances. But now you just have 2 tables that you have to update for every order. And it's starting to get a bit awkward. So let's say you wanted to add another feature like tracking reservations or like tips. So suddenly orders are now multiple steps that have to be linked together into one at the end for the final order in your invoice. And so basically we went from 1 table to like 3, and now we have to manage those and we have to figure out how to do like transactions and rollbacks. And now you have updating 3 tables. How do you optimize the query for that? So here you have to optimize 1, how the SQL is executed, and 2, how many statements that you can execute at once. And so now the problem becomes a bit more fuzzy and also becomes a bit more awkward. So we started off with 1 table trying to track transactions. Now we have 3, and I have to worry about the problems that we didn't really have before. And when I was doing this myself, because to learn about financial transactions, I was wondering, why is this so awkward? Why do we have to do all these multiple steps? Isn't SQL pretty much made for banking? And so I would look online and I figured maybe I'm just doing something wrong. But then tutorials online will just pretty much do the same thing here. So it's like, is this normal? So there's got to be a way to solve this at least somewhat easier and also somewhat more practical. So this is why I made Tiger Beetle. And so Tiger Beetle on its own is pretty much a distributed financial transactions database. All it is all that's in the name. So Tiger Beetle is open source under the Apache 2 license, and it's also written in an open source language called Zig, which is under MIT license. So Tiger Beetle is designed to be fast, like really, really fast. Like normal SQL databases from before, at least their inefficient versions, can handle like probably tens of thousands of transactions a second. Tiger Beetle at the moment can handle, I think, hundreds of thousands, and our goal is eventually 1 million transactions per second. So Tiger Beetle is also designed to be safe. So it doesn't matter how fast you can translate, or I guess handle money, if you start losing money or you start having data corruption. That would be pretty bad. And finally, Tiger Beetle is meant to be easy to use and a nice experience, not just for the people deploying Tiger Beetle, but for also the devs that are working on Tiger Beetle. I mean, it would be pretty well if we could have a good system that didn't have you fiddling with settings to set up and multiple build languages to use and stuff like that. So Tiger Beetle is designed from first principles, which sounds like a buzzword, but it's something you probably already do already, and it only comes down to 2 steps. So the first one is to just break down a problem into its fundamentals to actually know what you're trying to solve, and then start solving the problem from there. It's not really complicated at all. So let's go back to the previous example of tracking money. One thing we noticed is that anytime you try to make a financial system on SQL, you eventually converge into something that looks like double entry accounting. So in double entry accounting, each of the accounts have 2 columns that they operate on, so debits and credits. Debits is just money going out of the account, and then credits is just money coming in, but in accounting terms. The big thing about double entry accounting is that for every action in the book, there's always an opposite reaction. So anytime money comes in through credits, it must have gone out from somewhere else. And being able to track that somewhere else for every transaction that goes in the system, 1, makes it easier to flow at the end of the day when you want to check the book to make sure everything's right. And 2, it allows for computing balances really quickly. So in a double entry accounting system, a balance is just the sum of debits and the sum of credits for a specific book. It's pretty easy. And so the other invariant of a double entry account system is that the sum of debits and credits across all books must equal 0. And that guarantees that you didn't lose money along the way when you're trying to track it. So we are programmers here and not accountants. So instead of calling it books, we just call it accounts. And we just call 2 pairs of credits and debits between books transfers. So these are the only 2 primitives that Tiger Beetle uses, or I guess exposes to the user. So in code, that might look like this. The reason we don't have the balance for the account and have it a separate debit and credit sum is that there are certain accounts that allow you to have negative debit or negative credit, and we want the user to decide if their balance is correct based on that. So in code, that would look like this. Basically, a double entry accounting system is one where you have a set of accounts which have been operated on by a list of transfers. So we just add a API to interact with that, to create them and then look them up. And then we persist them to a database so that they don't get lost to time, and so that we don't have to have like a large working memory to store everything. And finally, we make it distributed so that if the database dies, then at least we have some other computer in the background that makes sure the data stays alive in case of like corruption and stuff. And so this is really all what Tiger Beetle is. It's just a distributed financial transaction database. And that's all the design. And it started from just figuring out what the problem is, tracking money, and how do we solve it just from that list alone. So tracking money in a way that's reliable, fast, and pretty easy to understand. And I'll try to convince you that's pretty easy to use as well. So before that, let's figure out how to make Tiger Beetle fast, because that's one of the big questions when we were trying to optimize SQL from earlier. So instead of SQL, let's look at the problems with it and why it didn't fit our use case in the first place. So in SQL, we had 3 tables to update for every order. And I don't think you can get rid of that in Tiger Beetle. There's always going to be multiple tables they have to update if you want a extensive transaction system. But at least one thing you can do is have multiple money transfers take pretty much the same amount of tables that you need to update. So instead of updating one transfer per multiple tables, you update multiple transfers per multiple tables. I mean, you can do this in SQL, but you have to re-implement rollback systems and re-implement transactions because it normally does it for you on a per insert basis. And that gets kind of complicated. Another thing we can do, since our focus is money and not necessarily data querying, is we can just remove the query language entirely. So since we're dealing with just accounts and structs, and I guess accounts and transfers, we can just make them structs instead of like having to parse an entirely separate language that may not fit our program model entirely, since we're just dealing with a ledger here. We're not dealing with custom data store. And finally, since Tiger Beetle is a transaction system, we're not really doing a bunch of processing besides making sure the ledger is correct. So we don't have to optimize for compute nearly as much as SQL does. So basically, we can just make our code single-threaded, which means no row locks, no having to synchronize between multiple threads, and none of that. It also makes the code easier to follow and makes it also deterministic, which will have some aids down the line. So with these constraints, we basically can't really use an SQL database to model Tiger Beetle if we want to be as fast as we claim. So we kind of have to write our own database. And so how does this database actually work? Well, the most easiest example to understand, and the one that's actually the most widely deployed, is with something like a B tree. So in a database, most of the data is just sorted blocks on the bottom. And then there's intermediary nodes between the sorted blocks that allow you to reach them without doing as many comparisons as the amount of sorted blocks below. So if you wanted to reach node number 4, you may only have to do 2 comparisons instead of 6 nodes down below. And so this works for single query access. We're optimizing that. But remember that in distributed, or I guess double entry accounting, most of the system is just a list of transfers. And it's also an immutable log at that. So you never go back and edit history. You always just keep adding more history. And if you try to do that in a B tree, you're going to have to keep traversing the tree to figure out where to add the next node at the bottom. And that traversal can add up to a lot of overhead. So we can actually avoid using a B tree here and use something called a log structured merge tree instead, or LSM for short. So in LSM, you have all the nodes as before, but you sort them into tiny blocks and then put them at the top. So the LSM tree is structured in a way where each part of it is called a level, and each level is bigger than the last one to hold more blocks. And so when a specific level gets full of them, or through other criteria, then you do a step called compaction, which looks at blocks which overlap between levels and tries to remove the duplicates and prefer the ones that are newer, and then compacts them into the next level. So this is how you maintain a set of updated blocks, but also have fast appending, which is like adding a new block to the top and then doing compaction later. But one issue with this is that if you put everything into the same LSM tree, then compaction has to sort through a bunch of unnecessary data. So like, let's say you only updated the balance of a specific account, and then you're having to compact that, and you're basically having to copy all the other parts of the account or all the other parts of the transfer into the new block, and that kind of wastes disk IO, especially also compute as well. Another issue is that there are certain parts of the account that get updated more frequently than the others. So the account balance, as before, it gets updated on every order, but like something like when the account was created, pretty much never gets updated. So that's also contributing to the wasted compute when we do compaction. So in Tiger Beetle, instead, what we do is we just have an LSM tree for pretty much all the different fields in account and transfers, as well as for account and transfers themselves. This removes most of the overhead of compaction, and it also allows us to query on those fields later when we want to expose the lookup functionality. So you could say that the Tiger Beetle's storage engine is like a little tree, or I guess a forest of LSM trees that we just look together to make the whole system work. So it's not enough to be fast. You also have to be safe, because no one wants to use a system that just loses money on you. And I've had that before myself. So you can't talk about safety without talking about memory safety, which is a pretty big topic now. So memory safety, it sounds unintuitive, but Tiger Beetle tries to verify this as much as it can. And it's kind of hard to do in a language like Zig, which is manually memory management. So we have a few tricks up our sleeves to make that work. So if you actually look at what memory safety is, it's split into two categories, temporal and spatial. So temporal memory safety is about making sure you access memory during the time that it's alive and not after. And spatial memory safety is about making sure you access the memory in the bounds that it's said that it's allowed to be accessed and not outside of those bounds. So we solve these in a few different ways. So for temporal safety, one of the issues there is you can actually access something after you free it or after you say that it's invalid to access. And how we solve that is with static allocation. So basically, Tiger Beetle never heap allocates while it's running. We just allocate everything we need up front and just use that for the entire duration of the program, which is a pretty odd tactic to use, because stuff like querying is you send a small data and it could send a large amount of data back. So how would you handle that when you have static allocation? And what we do there is just stream the data back in like pagination. So if you want a large transfer from a small query, we can just split the transfer into small blocks that you have to request multiple times so that we can still keep everything bounded. But that's only for double free. There's also a use after free, which is a type of free that doesn't necessarily conserve about memory. It's more about the logical access of the thing you're trying to verify. So example of use after free that isn't double free is like saying this integer is valid for this duration, but after that, it's pretty much garbage, and if you try to use it, it's going to mess up your program. So the way we avoid that is just have asserts everywhere in the code. Like half our functions is asserts, half the system is pretty much asserts. We write it like we're writing drivers. And this has a few benefits. One of them is that we can encode invariants that would normally be in comments in the source itself, and then just keep them there, like even during release builds. And it's not as expensive as you might think, given Tiger Beetle is single-threaded. But the other aspect of memory safety is bounds checks. So we handle bounds checks by deferring to the Zig language as well as the asserts, because Zig does automatic bounds checks for all arrays and all slices. And this makes sure that even if we got the asserts wrong, the language will still cover us after. The language also covers us for null pointers by having optionals be in the type system. So we can't accidentally do a null pointer deref, because it's always going to have us check it to make sure that we can use the value correctly. One of the things we do for safety, or at least the main thing we do for safety, is to make sure that the system is durable, or I guess your money is durable. So the way we do that in a distributed fashion is we just distribute the database to other computers, and we use a protocol called viewstamp replication to do that. It's similar to Raft and Pastos, if you've heard of those before. It's just a way to easier send data across the network and to make sure that all the data is synchronized. But VSR gives you the synchronization aspect, and it makes sure that the network won't fail on you, or if your node goes down and comes back up, then it can resync and everything. But it doesn't really save your data from being removed. What we can do here is that we can also rope in a storage fault model into VSR. So instead of just saying that this node is replicated, we can also say that if this node's storage goes down, we can fix it from the replicated nodes. And what allows us to do that is something called storage determinism. So because Tiger Beetle is single-threaded and deterministic, it allows us to know that if any other node ran the same double entry book, then they also should have ended up with the same storage on their copy pretty much. And so using that, we can say that if our copy gets destroyed, we know that everyone else's should be correct. And so we can ask them for the correct value. And with this, we can recover from storage faults, or we can recover from storage misdirects. Like if the disk messes up and tells you that your storage is right when it's wrong, we can still correct from that by just using under nodes. So to do that, we kind of have to mess up this little nice scheme that we had from before, and where everything's all abstracted. So the VSR protocol has to pretty much reach into the storage in order to make sure that everything's correct. So we have to add a little grid there just to make sure that we can fix the storage if it messes up. And the final thing we do for safety is we have a simulator. Remember that Tiger Beetle is deterministic. So that means that we can plug in pretty much any component that we want for any part of the system that we want and figure out if that messes up the entire system. So we do lots and lots of fuzzing and lots and lots of fault injection. So the deterministic aspect means that we can add in our own custom abstraction for the disk or abstraction for the network and like simulate faults, like dropping packets arbitrarily or messing up disk I/O at random and make sure that the system still upholds. We're even so confident about it that we have a GitHub bot which just continuously fuzzes the Tiger Beetle repo. And then once it finds a bug, then it posts a GitHub issue of it with a little stack trace to help us like figure out how to reproduce it. And we can always reproduce since it's deterministic. So we just put in the random seed and it'll always generate the output error, and then we just get to debugging that way. And if you're not aware, we also made the simulator a game that you can interact with in a browser using the link below. This is literally Tiger Beetle source code compiled into WASM, running in your browser, but then visualized using graphics. So this is the actual database running, in case you're interested and want to poke around and see if it's actually as safe as it claims. And finally, Tiger Beetle is meant to be nice to use. And one of the ways we do that is by making it a single binary. So when we compile Tiger Beetle, it's just one binary they have to deploy, and that's it. There's no extra configuration files. There's no extra like read replica they have to set up. It's just a single binary that you create the database file with, and then you just start it on the same database file. That's pretty much it. This makes the deployment process super easy. So you can use Docker, you can use Podman, you can use just even a native setup without too much hassle. We also added a little REPL so that you can connect to the database and pretty much play with it without having like to set up a custom like Python client or a custom Node.js client or anything like that. Just some quality of life improvements that we noticed were lacking from complicated systems in the past. Another thing that helps is the use of the Zig language itself. So in Zig, everything has no hidden control flow. So there's no operator overloading. There's no inherent like operator, like you can't make equal do something else, or you can't make a comma do something else, or a plus sign do something else. There's also no RAI. So all control flow is handled using some keyword of some sort. And this makes it easier to read and also easier to do code review. Another good feature of Zig is calm time. I was trying to think of a way to explain how good this is, but I don't think I can accurately represent the utility of calm time without you actually writing code. So if you're interested in Zig, I suggest you check it out and try to see what you can do with calm time. All I will say is that calm time makes having things pluggable so that we can do fault testing way easier than any language that I personally have experience with, and that's quite a few of them. And finally, Zig is pretty much the only dependency that Tiger Beetle has. So Zig is a C compiler, so we can compile C code. So we don't need stuff like Node GIMP for our Node client, or we don't need like a GCC for if we wanted to do a Python client or anything like that. We can just use Zig for all of it. Zig is also a cross compiler. So with the Zig executable, we can compile from any target to any target and vice versa. And finally, the Zig build system lets us use Zig like we would use CMake or we would use Gradle. Tiger Beetle experience is so nice that people have taken our components and made it into their own libraries. So someone took the IO stack of Tiger Beetle and made it into its own Zig library. And people use that, like unironically, to make their own services. And so we're kind of thinking of doing that for our VSR protocol, but that's like a thing down the road. So to recap, all we did is took a well-established financial system, like double entry accounting. Then we made a distributed financial transaction database from it. And that's pretty much all Tiger Beetle is. Just we have a problem and we solved it. And if you'd like to learn more about Tiger Beetle, you can go to this QR code down below. So thanks for listening.
Thank you so much. Before we take Q&A, Richa, yes, could you please set up now? We'll take the one question while you're setting up. We don't have a 5-minute break between talks. Okay, do we have questions for King on Tiger Beetle? He has covered the subject so completely that there is nothing left to ask. I have a question.
Hey, sure.
So the usual accounting structure is that you've got accounts and entries, and the entries are grouped into a transaction because there's no assumption that a transaction only affects 2 accounts. It can affect an arbitrary number so long as it's in balance. Does that work, or does that require redesigning the definition of the transactions?
Not necessarily. That can be fit into double entry accounting by using multiple accounts, or we can use our batching system before. So remember, Tiger Beetle has a way to
the batching system is the answer. Because yes, if you're selling a thing, then there's an entry for account receivable or cash paid. There's an entry for goods sold, but also shipping expense, GST, right? And all of those have to happen together or not happen at all.
Yes, so our batching system lets you link transfers between each other and evaluate them as completed or not completed. And that lets you represent multiple ways of doing multi-transactional systems.
Okay, it's a workable approach. All right, thank you, King. Finally, last but by no means least, we have, am I in the right place? Richa Gaur from Microsoft to talk to us about the cosmos. Assuming that the technology gods are with us.
Hey, hi everyone. How are you doing? Yeah, nice to hear you. Yeah. I'm Richa Gaur. I'm a product manager at Azure Cosmos in Microsoft. And today I'm going to be talking about as a developer how you can go from onboarding to production on our new SQL database using Azure Cosmos. So today's session is divided into 3 parts. First, we will set up Cosmos DB. This will include data modeling, partitioning the data, and estimating capacity to provision the container. Secondly, we will figure out how to use the SDKs to develop our client-side applications and do some optimizations which can better application performance. And finally, we will hit the production. And before hitting the production, we will ensure that our application is highly available and we are set up monitoring and logging correctly. So let me give you a quick introduction about what Azure Cosmos DB is. It is a fully managed database service by Azure, which means that all the infrastructure is taken care of by us for you. It is multi-API database. We have our core NoSQL offering where you can query using SQL, and we also have compatibility with open source APIs like MongoDB, Cassandra, Gremlin, Postgres, so on and so forth. Finally, we provide global distribution on turnkey basis, and we provide high performance and high availability that is backed by comprehensive SLAs. So for today's talk, let's take an example of a real-world logistic applications, whose simplified architecture could look like this. We have two scenarios. First is write heavy, where we will ingest IoT data at a very high rate, so that we get the real-time status updates from the vehicles in our fleet. And second is the read-heavy scenario, where we have a web application to monitor the status of vehicles, consignments, packages in the fleet. So here we will read the data from the database. Although you can see there are multiple components in this architecture, but we will only focus on Cosmos DB for this scenario, for this talk. Yeah, so before we begin developing the application on Cosmos DB, let me give you a quick intro on why we should use Cosmos DB in the first place. And answer is that if you have one or more of these requirements, then it's probably the right fit. You should have, so if you need the flexible schema, so in our case, we have sensor data which can change over time. Today it is 8 fields, tomorrow it might be 7 fields, or it will take 10 fields. And you don't want to deal with the chaos schema migration. So flexible schema is what we get with the JSON document format that Cosmos DB supports. Second is scalability, especially for writes. Our use case need high writes because the IoT data and Cosmos guarantees throughput for any workload, no matter how small or how large it is. Finally, we want our application to be very fast. We want real-time updates. And with Cosmos, you get 399 guarantee of less than 10 milliseconds for reads and writes for a document of 1 KB.
And our application needs to be highly available because we don't want to lose status of our vehicles in the fleet. So looks like Azure Cosmos DB can cover the use case for today. So let's quickly set up the Cosmos DB. So you can start by choosing the API that you want according to your use case. We will continue with the NoSQL API. How is this? So sorry, but it is moving by itself. So all you need to do is provide the account name, the region in which you want to create the account, and the capacity modes, whether you want a serverless account versus a provisioned account. The resource model is pretty simple. We have the top level entity account, then we have databases, and within that containers. Think of containers as tables in relational world, and the data is stored in JSON format, which gives the schema flexibility. Finally, to create a container, all you need to do is provide the database name, container name, which is easy. Then we have partition key. What exactly is that? We'll talk about that. And then you need to provide the capacity. So sorry, I think something is happening with the slides. Okay, is it visible correctly? Yeah, okay. Yeah, so yeah, finally we need to provide the throughput, which is basically how you set up the capacity for the container. And that's all. That's how you can create the container and start using the Cosmos DB account. Talking of capacity, request units is how you configure capacity in Cosmos DB. It's nothing but an abstraction or a currency over the request or over the resources that a request needs in order to execute, like memory, IOPS, CPU, etc. So it's the abstraction that we provide from our side, so that you have to only think in terms of one resource, not multiple. And finally, it can be provisioned both at database level and container level, which means that you can have dedicated throughput for a container, as well as you can get shared throughput when you configure it at database for multiple containers. Let's quickly see how you can find RUs using SDK. So this is what a sample telemetry document looks like. It is a JSON document of 15 properties or so. So this is a snippet of my IntelliJ IDE. What I'm doing is I'm using Cosmos DB Java v4 SDK. So I'm writing the code in Java, but we have SDKs available in all the major languages like Python, Node.js, Golang, Java, and .NET. So all you need to do is, all I'm doing is just writing the document in the container and getting the response, getting the request charge from the response, and similarly reading the same document and getting the request charge from that. So when I run this code, you can see that the request charge it took to write one item is approximately 10 RUs, while it took only 1 RU to read the same document. So for our use case, let's try to estimate the capacity that we need for the container. So assuming that our Contoso logistics application has 1,000 vehicles in the fleet, and we send one document every second, that means that we need the capacity to write 1,000 documents per second, and each write consumes 10 RUs. That means that we need 10,000 RUs per second. So this much capacity should be enough to basically get the data from all the vehicles in our fleet. We also have a capacity calculator, which is just a fancy UI on top of these calculations. It lets you estimate the RU capacity and also shows the associated cost based on the provisioning models. Now that we have understood the capacity, how to estimate the capacity, what exactly request unit is, let's understand what types of provisioning model Cosmos DB provides. So Cosmos DB provides multiple provisioning models based on different use cases. So in case you don't want to deal with the capacity estimation at all, or you are just starting out developing your application and don't know how much resources it is going to consume, what you can do is you can provision a serverless account. There is no need to estimate any capacity for that. It's a consumption-based pricing model where you only pay for the throughput that you are going to use. So it's quite good for customers who are just starting out on Cosmos DB, or who are testing their workloads, or who have very infrequent access to the database so that it's mostly idle. So all you need to do is just choose a serverless account while creating the account. Coming to provisioned model, we have two provision models. One is the auto scale. So auto scale is basically a provisioning model where you configure a capacity and you can scale between 10% to max of that capacity instantaneously. And you only have to pay for the throughput that you are using in that particular moment. You don't have to pay for it all the time. So for example, you're using only 40% capacity at any moment, then you only need to pay for 40%. And rest of the time it can stay at only 10%. So it's quite good for the use cases where the traffic is unpredictable. It changes so many times in the day. It's difficult to predict that. So you really don't need to, break your head around estimating the capacity and always paying for maximum resources. Finally, we have manual provisioning mode, which is good for predictable workloads, and it's quite cost friendly and easy to configure. This is a fixed capacity that you configure and which is available and payable at all the times. Moving to partitioning. Partitioning is a core concept in horizontal scaling. So do you remember that when we were creating the container, it asked for the partition key in the list of things that you needed to provide? Yeah, the reason is because partitioning is the key to scaling. We ask for partition key because that's how we distribute data to multiple nodes, so that so that the container can scale horizontally as opposed to vertically, where you use only one large machine to store all the data. So as and when you add more data, the containers keep scaling up and adding more and more nodes to accommodate that capacity. Think of it as like working in a team where we have different team members and all the workload is equally divided among all the team members. So this is how the data distribution model looks like. So whatever partition key you define, the documents belonging to the same partition key will always go to the same logical and physical partition. These are different physical partitions. So this is how basically the data is distributed. So it's very important that we choose the right partition key, which ensures that the data is equally distributed, and also the requests are equally distributed among all the partitions to to maximize the throughput that you can get out of the database. So the general best practice from our side is that for write-heavy workload, you should use a partition key which has very high cardinality, so that you can concurrently access the data from multiple physical partitions at the same time. And for read-heavy workloads, you should always do key value lookups where you can, query with ID and partition key, so that exact document is fetched from the container instead of going to the query engine and finding the document. It always consumes one request unit. And finally, for queries, you should always include partition key in the filter, so that the query is directed to one specific physical partition, so that the querying is fast as well as less resources are consumed to execute the query. So let me show you a quick demo of how a good versus bad partition key makes a difference to the application's performance. So I have one container which V1, which has ID as partition key, and the next container V2, which has ID as username. So both the containers have the same data, exact same number of documents. The only difference is the partition key. So what I want to do is I want to find out the documents related to a username called Tori Bahringer. So when I query this against the V1 container, you can see the request charges took is 82. While in the second case, when I query it against V2, where the username is the partition key, and also the filter in our query is also partition key. Username. So it took only 62 RUs. This difference can become huge if your data size is large. So that way it becomes important that you choose a partition key which is efficient for your queries, so that you end up doing single partition query instead of fanning out the queries to multiple partitions. Now that we have understood the core concepts and set up the Cosmos DB, let's move on to do the development which from the client side. First thing that we need to keep in mind is whenever you want to do a key value lookup in Cosmos DB, you should always use point reads, which is an API in the SDK. So here we are using the read item API, where you need to supply the ID, which is unique, and partition key. So with this, this always consumes 1 RUs, and it takes very less time to execute point reads, versus when I find the the same document using the query, it not only consumes more resources, it also takes more time. So it is advisable that you always use point read API to do the key value lookups. Although we have emphasized that you should use single partition query and always use the partition key in the filter, but there can be situation where you want to use cross partition queries, and in those scenarios you should take full benefit of the parallelization that our SDK can offer. So for that, you can set the max degree of parallelism to -1, which lets the SDK optimize the number of threads required to perform the query based on the client configuration, so that it can parallelly execute the query to the physical partitions in the backend. So there is, so you have multiple threads as optimized as possible based on your client configurations, which are parallelly querying all the physical partitions in the backend. While so this gives you better latency and performance. Versus in the second case where we are using a finite degree of parallelism, it limits the number of threads, or in some cases it can choke the client side resources to do the parallel queries and end up losing the parallelization benefits. So you should let SDK take that optimization call from its side by setting the degree of parallelism to -1 to concurrently perform cross partition queries. Finally, moving on to writes, Cosmos DB by default indexes all the fields in the JSON document. While it is very convenient that you don't have to think about indexing at all when you are changing the schema, it can become an overhead when you are writing the document, because you have to always update the indexes associated with all the fields. So this is what a default indexing policy looks like. Here we have indexed all the paths. So what you can do from your side to optimize the writes is tune the indexing policy so that you only index those fields which are required for the queries that you are going to execute in your application. So here we are just indexing 3 fields while we are excluding the rest of the fields from the JSON. So let's see how this makes a difference to the write performance. So when I write a telemetry document using default indexing policy, it takes around 15 RUs. While when I write the same document using the tuned indexing policy, it only takes 7 RUs. So that's approximately half. This lets you cut your throughput capacity into half and gives you better performance in terms of both latency and the resources required to execute a write. Finally, moving on to monitoring the performance, Cosmos DB provides certain default metrics from our side so that customer can take advantage of these default metrics. So we have metrics related to request, which can be filtered with status code, operation type, container name, database name, anything you want. And then we have metrics related to throughput, which lets you monitor the resources consumed by a particular request. It can be again bifurcated by status code, operation type, so on and so forth. Then we have other metrics related to storage, availability, latency, and other things. So all of these all of these metrics, while are available on the portal, Azure portal, we also have APIs to access these metrics from the SDK itself. So you can create your own dashboards and custom alerts on top of these metrics without actually writing the code to fetch the get the metrics from the responses. So that's pretty convenient. And while these metrics are aggregated metrics, these are aggregated on a minute level or a 5-minute level period. We also have metrics related to each request, which can be enabled differently using log analytics. So finally, we are ready for production now that our application development is complete and we can monitor it. But before moving to production, we need to make sure that our application is highly available. Our database application is highly available. And for that, what we need to do is add a second region for high availability. Adding a second region gives 5 nines of availability, which is just 5 minutes of downtime in a year, which is pretty good, right? So yeah, with single region, you get 4 nines of availability, which is 52.6 minutes in a year. And with second region, you get 5 nines of availability, which is just 5 minutes. All you need to do is just add another region from the globe that you can choose, and you have 5 nines of availability for your database service. So finally, to summarize, you need to set up the service right by choosing the right API. By choosing the right API, designing the data model appropriately for your application, and tuning your queries, and choosing the partition key which is efficient for the maximum queries in your application, and estimating capacity. Then while doing the development, you should take care of all the client-side optimization that SDK provides. And during testing, you can test it using the local emulator, which is just a desktop version of Cosmos DB, which you can download for all operating system and test locally. It is exactly the same. You will get exact same responses, exact same request units that would be consumed. So you can do the testing locally. And finally, before moving to production, make sure that your database performance is as expected through the metrics, and set up another region for high availability. Yeah, that's pretty much it from my side. Thank you, folks.
Thanks very much. We have no further speakers, so no more awkward setup. But questions, anyone? Aha.
This question might be too simple for this talk, but I'm a bit confused about the concept of indexing policy. So if you could explain a bit more about what is indexing policy?
Yeah, so it's pretty similar to what indexing is in a SQL database. So in SQL, you create primary keys, and then you create different indexes. In Cosmos DB, the indexes are by default created for you. Like when you ingest a document, all the data is indexed by default for all the fields have the index. So that is what the default indexing policy is. It gives you the flexibility of adding new fields in the JSON schema and not thinking about indexing or creating the indexes. But you can also optimize the indexing policy according to your needs, so that your writes are more optimized. So that way you can, how you can do that is just include the fields that you need to index and exclude the rest of the fields. Or you can do it otherwise as well. You can exclude you can exclude certain fields and include what you need.
So the important change, or an important change, is that the default index set is not empty. So most relational databases by default index nothing.
By default, it is all.
In this case, you're indexing by default all.
Yeah.
So there's a reason to
tune the index.
It's an optimization step to optimize the write cost rather than the read cost. That's quite clever. I have a question. You have a sort of unified way of dealing with either provisioned or serverless deployments. Having created a database, whatever it is, can you transition between serverless and provisioned? And if so, how long does it take and what does it cost?
Yeah, that's pretty good question. So we are just rolling out this feature in May. So from you can start out with serverless and then move on to provision when you have a better control of your capacity requirements. You can definitely migrate to provision. It's an in-place change.
Both ways?
We also have both ways that will be coming out in September. So okay. we are rolling out serverless to provision in May.
Fantastic. Any other questions? Going once, going twice.
Thank you, folks. We also have a virtual conference called Cosmos DB Conf. It will be happening on 16th of April. In case you are interested about Cosmos DB or any specific topic in general, you can watch this on YouTube and live or on demand. So you can probably register for it as well. Thank you.
Very cool. Well, that concludes the final talk on this track of the conference. And in fact, the final session of the conference starts downstairs in 5 minutes. It's the final commit. Yes, this has actually been a distributed version control problem. Please join us in the main hall downstairs in a few minutes' time for the wrap-up session for the conference. Cheers. We have some
Okay.